So in a previous video, I talked about how I liken inductors to toddlers. They resist changes, and the quicker you try to change, the more they try to change it, or try to oppose it, I should say. So what I'd like to do now is take a couple minutes and talk about an RL circuit. This is an important circuit. And at first, I'm just going to sort of convince you qualitatively what happens to the current and the voltage, and then we'll actually derive it. So on most APC problems, frankly, you don't need to derive it, but it's useful to know what the current versus time looks like in this graph and what the voltage across that inductor looks like versus time. So imagine the circuit is open and there's no current flowing through, and then I close a switch or something, so now the current is going from 0 to ultimately some higher value, but it can't do that instantaneously. That's the most important thing here. So when you turn it on, there's going to be a current that goes like this, and that current goes like this, and then it's going to go and it's going to curl around. Now by our right-hand rule here, we know that if that positive current curls over the top, the magnetic field is going to be pointing to the left. Let me just use a different color. Like so. And that magnetic field will grow as the current grows. The problem is, inductor doesn't like change. So what it's going to do is it's going to try to, by Faraday's law or Lenz's law, it's going to try to oppose that change. It's going to try to create within it a magnetic field that opposes that. It's smaller than the existing magnetic field, but it's going to oppose that. To do that, it needs to establish a potential difference that is going to try to oppose that change. So in this case, we're trying to increase the current, so it's going to try to decrease the current. It's almost like it's trying to make this current flow from right to left, almost like you're trying to make this a positive side. I'm sorry, this a positive side and this a negative side. That induced voltage, we learned, is negative L, the value of the inductance for the inductor, dt. And that inductance depends on things like the geometry, basically. How many coils per length, what the area is, things like that. So qualitatively, you can look at this and you can say, well, the current in the beginning is going to be fiercely opposed, so there's not going to be any current flowing at all. And then it's going to build, but as it builds, it's going to build more and more and more slowly. And you wind up with this relationship. You may remember this kind of shape from capacitors. That looks like something that starts at 0. So first of all, the initial or the ultimate value that it's going to reach is E over R, Ohm's law, the battery over the resistance, as if there was no other elements in the circuit. And you're always going to be some fraction of that. In the beginning, you need it to be 0, and in the end, you need it to be 1. So it's like 1 minus an exponential decay. That's 1 minus e to the minus L over R times t, like that. I mean R over L, sorry. And the voltage, similarly, in the beginning, the voltage of the capacitor, or the voltage of the inductor, rather, is going to be the same as the battery voltage, but in the opposite direction, opposing it. And then it's going to exponentially decay. So that's going to be E, the battery voltage, times E to the minus R over L t. So that's going to look sort of like your regular decay, sort of like that. So very similar to what we saw for capacitors. If it's just a matter of remembering it for a multiple choice question or invoking it, understand this. Capacitors, inductors, very heavily tested, really important. But sometimes it does come up, and frankly, it's an enjoyable experience to come up with this equation ourselves. We can do that. We do that like we do with many circuit things by just sort of looping around the circuit and making sure the voltage drops around the circuit add up to 0. So let's say this battery has a voltage of E. And we're going to start at the battery, and then we're going to go through the resistor in the same direction as the current. So that's going to take energy away. That's E minus IR. And then we're going to go through the inductor. And that inductor is going to lower the potential difference. It's opposing us. So it's going to be negative L di dt, and that has to add up to 0. Now, in terms of energy, what's going on is you're losing some of the energy through thermal loss, just heat in the resistor. And what's this? This is actually storing energy in the magnetic field of the inductor. And maybe we'll come back to that later. But now we have a similar situation when we had capacitors charging and discharging. And we're going to rearrange some things and do some math. And, a lot of this math is going to look really, really familiar. So first thing I'm going to do is, all right, E minus IR on this side is going to equal L dI dt. And we're going to try to get into a situation where we can separate variables. So I'm going to bring the L over here. So that's 1 over L dt equals 1 over E minus IR di. And you can see on the left when we integrate, that's going to be pretty simple. But on the right, so we're going to integrate both sides. In this case, we're going to go from 0. I'll use capital T, where capital T is the time at which we want to know the current. And here we're going to go from a current being 0 to a current going, I don't know, I'm just going to call it capital I for the current at the time that we want to know about. Now, on the left side, we'll just cut straight to the chase here. You integrate dt from 0 to t. That's not that complicated. That's just t, and we have that constant L. Now, on this side, what I'm going to do is I'm going to say, huh, that looks kind of familiar, but not exactly. I'm going to take this, I'm going to call that U. So U equals E minus IR. Well, that's not an I. That's an I. du is going to be negative R di. And because we're trying to replace this, di is going to be negative 1 over R du. So what I'm actually going to integrate is going to be the integral from, I don't know how math teachers like to do this. I'm going to call it from I equals 0 to I equals capital I. And we're integrating 1 over U du. Well, the integral of that is the ln of U. Now, I'm going to skip a step here. U, we just saw, was E minus IR. So we're taking E minus IR, the ln of that, from I equals 0 to I equals capital I. Now, can't forget the multiplying by the du. Now, the du in this case was, let's see, negative R du, and obviously the du went away. So, okay, T over L. So this winds up being the ln of E minus capital IR minus the ln of E minus 0 times R, or E. I'm also going to bring over this negative R. So I'm really not trying to be confusing, but I see what I did there. It was supposed to be 1 over R. I'm going to put it out here. And when I bring it over here, that's going to be T times negative R over L. And of course, log rules, this is the same as the ln of E minus IR over E. And then we're going to exponentiate both sides. When you e to the ln of something, you just ignore the ln. And this is now E minus IR over E. This is E to the minus RT over L. Cross multiply. So that's E times E to the minus RT over L equals E minus IR. Getting a lot closer. We want to get I by itself here. So this is going to come over here and be IR. And this is going to be, I'm going to skip it in one step. That's going to be E times the 1 from the right side. And we bring this over. It's minus E to the minus RT over L. And that's I equals E over R times 1 minus E to the minus R over L T, which is exactly what we thought it should be. It's some fraction of the current you ultimately end up with, which is E over R, the same as you would get if it was just a battery and the resistor. So in the beginning, that current is 0, and in the end, it winds up being this. Now, you'll often see this written instead of R, let me just use a different color here. Instead of written this way, you'll often see this written as E to the minus T over tau L. And of course, tau L is L over R. And that time constant means a similar thing to what it means with RC circuits. So after 1 tau, this should be T. After 1 tau of time, you're left with e to the negative 1, or 1 over e, or 36.7%. Now, what if we wanted to know the voltage of the inductor? Well, we saw that the voltage of the inductor, or the E of the inductor, is negative L di dt. Well, what's di dt? That's the same as negative L E over R times d dt of 1 minus e to the minus r over L t. So, well, what's the derivative of this? We can ignore that, and then this winds up being the same thing, negative e to the minus r over L t times the derivative of that, which is negative r over L. So let's see if I can put all this together properly. Yeah, sorry for mixing little r's and big R's. It doesn't really mean anything here, but negative L e over R times this is positive e to the minus r over L t. And then we've also got an r over L. These cancel. This R, this L. And you're left with the voltage across the inductor equals negative E times e to the minus r over L t, which is what we expected. It's always some fraction of the battery voltage, but in the opposite direction. So it starts off equal to the voltage of the battery, but opposite, and then decays to 0. So if you ever have to, that is how you approach an RL circuit. If you ever have to do an inductor in a circuit like this, my strong advice is to consider looping around the circuit and adding up the energies, and they still have to add up to 0. So good luck.